Right. Hey everyone, welcome to the July meetup. It is July, right? Yeah. Wait, no. I knew I messed up. Yeah. Right. Yeah, that never happened. I know how to time, I think. All right. Hey everyone, welcome to the June Rust meetup. As always, thanks Mozilla for hosting and the food and stuff. Next month, we will probably be in Stanford. Maybe. The meetup's still being put together, but like I said a couple meetups ago, we're thinking about moving it around so that more people can come easier and it's good. And also, it's easier if I don't have to organize every meetup. That way I don't make mistakes like July. All right, just one quick announcement. The Rust book is now in stores. This is the one that's online, but you can get a paper copy as well. This is the one by Steve and Carol. So yeah, that's the first print copy, I guess. Like Steve had it a few weeks ago, and now it's out for everyone. So yeah, you can grab a copy on Amazon or No Starch Press or somewhere. I don't know. You can find it. It's not hard. Yeah. So today we have two talks. We have Sunjay talking about coherence in Chalk, and we have Raph talking about data-oriented GUI in Rust. So I'll hand it over to Sunjay. Sunjay has been working on the Rust project on and off for a while, and he's also an intern at Mozilla working on Chalk. He's mostly going to be talking about his intern project, right? Yeah. Cool.
Okay. Do we have slides? Wonderful. Awesome. So hi, everybody. So as Manish said, I'm Sunjay. I actually only started working at Mozilla a couple of weeks ago, and I've had the pleasure of working on this project called Chalk. Chalk is the new trait system implementation in rustc, and my research mainly focuses on modeling coherence in Chalk. Don't worry if you don't know what coherence is. I'm actually going to talk about it as I go along. So I'm going to start this talk by talking a bit about what Chalk actually is. Then I'll go into coherence and what that means in the context of the Rust programming language. After that, I'll talk a bit about logic programming and cover how we lower Rust code into logic in Chalk. Finally, we'll talk about two parts of coherence, the orphan check and the overlap check, and I'll finish the talk with a summary and some final thoughts. So let's start with Chalk. There we go. So, sorry about that. There we go. So Chalk is like I said, the new traits implementation in Rust. But here's how the current Rust compiler looks at about 10,000 feet. So the compiler takes your Rust code and runs it through some very cool stuff in the current traits implementation, and then eventually, after a couple more steps, outputs machine code. Chalk is the new traits implementation. It uses logic programming, and the idea is that we can take the logical rules that the trait system abides by and represent them with logic programming. I'll tell you more about logic programming in a little bit, but for now, let's talk about the part of the Rust trait system that I'm personally focusing on. Coherence is all about making sure that there's only a single implementation of any given trait that applies to any method call at a given time. So it's responsible for a lot of the really cool properties that our trait system has that other languages actually don't have. So what that means is that if you call the fav method from the favorite color trait, we want to match that to exactly one implementation of that method. We want to make sure that you can't actually even define two possible implementations of a method for the same types. Fundamentally, coherence means that no matter what, given a trait and some set of type parameters, there should be exactly one impl that applies. This is important because if we have this property, then no matter where your traits methods are called, you can be sure that the behavior will be exactly as you expect. And Rust's coherence guarantees actually apply across crates as well. So even if you add a dependency to your project, it's important for that dependency to never be able to introduce a conflicting implementation of any trait. Coherence enables Rust and Cargo to actually do a lot of really cool things. Rust is able to allow multiple distinct versions of crates in the dependency tree of your project. We avoid what's known as the hash table problem, where different underlying impls are selected for the same operation in different contexts. You can imagine that if a different implementation of hash was chosen for insert versus when you were getting something from the hash table, that would cause a lot of problems. So coherence makes it so that we can never split the ecosystem by having multiple incompatible implementations of the same types in two different crates. Crates are able to maintain backwards compatibility and add impls without increasing their major version number every time. If some other crate could implement methods for your types, this just wouldn't be possible. An often requested feature in Rust is specialization, and the only reason specialization is actually possible in Rust is because coherence makes it so that there's only a single choice for a method's implementation at any given time. If two crates that are compiled separately could have overlapping implementations, then we wouldn't be able to implement specialization. So coherence means that for any given trait, there are either 0 or 1 impls of that trait that apply to a given set of types. No more than that. That means that the myTraitFoo method here maps to just one implementation. Coherence also means that for every impl that could exist, it only exists in one place. And this is key for having a coherent system. In this example, that means that only one crate has the power to define this impl of my trait for any type T. If you'd like to learn more about coherence and hear the things I described in much more detail, Boats, who's known as Without Boats on GitHub and Twitter, gave a fantastic talk at a meetup last year, which covers coherence in detail. So how does the Rust compiler enforce coherence? Well, coherence is implemented as the combination of two checks, the orphan check and the overlap check. The orphan check is designed to ensure that every impl abides by the orphan rules, which we'll talk about in just a minute. This check is what gives us the property that every impl exists in only one place. The overlap check makes sure that every pair of impls can never apply to the same set of types. This check allows us to guarantee that there is only up to one impl of a trait for a given set of types. The orphan check goes through each impl in the current program and tests to make sure that it abides by the orphan rules. Now, there are actually a lot of different sources about the orphan rules, and I definitely suggest you check some of these out if you're interested in learning more. But when it comes to the Rust compiler and the Rust language in general, the most authoritative source is often actually the source code of the Rust compiler. So let me show you some of the files and functions where the orphan rules are implemented. There's the orphan checker, which actually describes how rustc goes through each impl in order to check it. There are the orphan check and orphan check trait ref functions that actually do the heavy lifting of checking that an impl satisfies the orphan rules. And while we don't actually have enough time to dive into the code for each of these functions, what I've done is I've gone through them and extracted the orphan rules exactly as they're implemented in rustc today. So here, without any further ado, are the orphan rules according to the source code of the Rust compiler. Ta-da! Now, this is a whole bunch of words, and it's written to be very precise. It's written to be a very precise mathematical definition of the orphan rules. And originally, when I was designing this talk, I tried reading them out loud. And it turns out that reading math out loud is a terrible way to explain things, and it's literally impossible to understand. So we're actually going to skip all of this, and I'm going to explain the Orphan Rules in a much more visual way that I hope will be easier to understand. So the Orphan Rules are centered around impls. An impl describes the implementation of a trait for a given type, and impls can have 0 or more type parameters, and the trait itself can also have 0 or more type parameters. One thing I've done, which is going to come in handy later, is I've labeled the implemented type as P0 and labeled the type parameters of the trait as P1 to Pn. Now let's talk about why I did that. So the Orphan Rules start by asking whether the trait we're implementing is defined in the current crate or if it comes from a dependency and is thus an upstream trait. If the trait is locally defined in the current crate, the Orphan Rules say that it's good to go, and we can implement it for any type at all. But if the trait is an upstream trait, then the Orphan Rules say that we need to check a few more things. The first thing we have to check is that there's at least one type from P0 to Pn that's locally defined in the current crate. Part of the definition of the Orphan Rules is that we actually start searching from the implemented type and then go through each type parameter in the trait in order. I labeled those types from P0 to Pn, so it's easy for us to remember to do that. Once we have a local type, we check each type before that and make sure that it doesn't contain any of the type parameters T, U, V, etc. If all of this can be verified, the impl is valid and we can continue. But if any of these steps fail, the impl is considered an orphan impl and it's disallowed by the Orphan Rules. So if these rules seem kind of strange and arbitrary, it's because they sort of are. And the resources I linked to earlier go into the history and the reasoning behind them, and they talk about why they work towards our goal of having exactly one place where an impl can belong. But for now, just try to keep these rules in mind because we'll come back to them later and talk about how they get implemented with logic programming in Chalk. The other part of coherence in Rust is the overlap check. This goes through all pairs of impls and checks for any overlap between them. The tricky part about this is that in order to enforce coherence, we have to be able to check all possible impls in the entire universe. In other words, we need to be able to check any impls that could exist in any compatible world. And the reason that we're only interested in impls in Semver-compatible worlds is because if we tried to just support everything, our rules would be way too restrictive. Okay, so that's a lot of information. Let's take a break from coherence and talk about logic programming. So in logic programming, the idea is that given some facts and some rules about those facts, we can come to conclusions by proving things based on what we know. Take, for example, the sentence, Sunjay loves cake. I'm Sunjay, I love cake, right? This is a fact, and I can write this in emojis like this. Cake is pretty sugary, so if I enjoy cake, well, it might be reasonable to think that I enjoy candy as well. We can write this as a general rule using emojis like this. Notice how I've left a placeholder to represent that this rule applies to anyone who loves cake. This is a general rule that says that blank loves candy if they love cake. We can take this fact and this rule and use them to derive the conclusion that Sunjay loves candy. We took the rule that says that someone loves candy if they love cake and used the fact that Sunjay loves cake to come to the conclusion that Sunjay loves candy. And I can tell you from personal experience, both of these things are true. So this is provable because we can logically derive it from the rule we created using the fact that I love cake. Chalk's logic programming language is actually based on an extended form of a well-established logic programming language called Prolog. If we wanted to represent the same logic we showed before with emojis, we might write something like this in Prolog. Here we've represented the same fact that Sunjay loves cake, but we put the loves part on the outside and the Sunjay and cake parts on the inside. It still represents that same sentence, it just uses a different syntax. Previously, we were using the heart emoji to represent when someone loves something. Here, we defined a predicate using the word loves to represent the same thing. And after that line that represents Sunjay loves cake, we even have the same rule about candy that we had before. The colon followed by a dash is how you represent the word if in Prolog. So just like before, this rule reads as T loves candy if T loves cake. T is a variable that represents anything that could be placed there. Now, if we ask whether Sunjay loves candy, the answer that Prolog produces is yes. This is the same conclusion we came to before, and Prolog has reached it in a similar way by using our facts and our rules to prove the answer to our question. Chalk's logical language is actually even more powerful than Prolog on its own. Chalk supports a number of interesting features such as for all and exists. And for all means that a given rule is provable for all values of the variable t, whereas exists means that a given rule is provable for at least one value of the variable t. This allows us to express things like each type t implements my trait, or that there is at least one type t that implements my trait. Okay, so now that we know some basic parts of logic programming, let's talk about how Chalk takes your Rust program and turns it into logic. I mentioned earlier that Chalk is the new trait system implementation and that it uses logic programming to model the rules of the trait system. Well, lowering is the name of the process in which Chalk takes each declaration in your program and turns it into logical predicates that are similar to what you saw before. When we're lowering, we can take anything that we know about the program and use it to produce facts and rules, just like we did when we were talking about cake and candy. Let's say, for example, that we're compiling a crate called people. The people crate depends on another crate called favorites, which defines a struct, a trait, and implements that trait for any type that implements copy. Both people and favorites implicitly depend on the std crate, which defines some traits and types of its own. Using the favorite color trait from the favorites crate, people defines some of its own implementations of favorite color for its own types. This gives us the complete program shown on the left. Now what Chalk wants to do is it wants to lower this entire program, that means all three crates, into a single logical program made up of facts and rules. There's a whole bunch of facts that we could actually potentially get from this program. For example, we could describe the relationship between the crates and add something like depends on people favorites to talk about how the people crate depends on the favorites crate. Or we could add some clauses like defined in Sunjay people or defined in Manish people to describe how those two structs are defined in the people crate. These are hypothetical, but my point is that you can lower a program into any set of facts that you can derive from it. In reality, Chalk would lower the program into something that looks like this. I've filtered out some of the facts that aren't relevant to what we're about to talk about next, but you can probably see where most of this information is coming from. I mentioned that we're currently compiling the people crate, so the Sunjay and Manish types are local to the current crate. Chalk represents this by lowering these two structs into two facts using the isLocal predicate. We lower the two implementations of the favorite color trait by adding two facts using the implemented predicate. The taco type, which is defined in the crate that the current crate, the people crate, depends on, is an upstream type. We can lower it to represent that with a fact that uses the isUpstream predicate. Notice that each of these predicates represents a concept that we can clearly see in the code. The reason that any of these exist at all is because we decided that they're important, and we decided that there's something that we needed to use in order to model whatever we're modeling. We literally could have created any predicates at all based on what's in the program. The final line of this lowered program is probably the most interesting. There, we create a rule that describes that any type, T, implements favorite color if T also implements copy. You may not see it perfectly just yet, but it's pretty amazing that we're able to take the Rust code on the left, extract its essence, and put it into the logical representation on the right. In the next section of this talk, we're going to see how this allows us to elegantly represent the very complex orphan rules that we described earlier in terms of logic. So there's a lot of details about chalk and the lowering process, which I couldn't get into today. But if you're interested in finding out more, the online rustc guide actually has an entire section on the new style trait solving implemented in chalk. Okay, so remember all that stuff about the orphan rules? We're going to bring everything together now and talk about how the orphan check is actually implemented in chalk. Before we start, though, let's quickly do one more example of the orphan rules to make sure that we've definitely got it. Let's say that we have a crate foo, which defines a trait called myTrait, and a type foo. We also have the bar crate, which depends on foo and defines its own type bar, as well as an impl of myTrait for bar. The orphan check will look at that impl and try to decide if it's valid under the orphan rules. When we compile bar, myTrait is considered to be an upstream trait. That means that based on the orphan rules, we have to do some more checking. We can't just implement that type directly. We have to check foo, bar, and then t in order to look for a local type. In this case, the first local type in the bar crate is the bar type. And once we find that, we need to check every type before it to make sure that those types don't contain any of the type parameters of the impl. The term we're going to use for types that don't contain any of the impl type parameters is fully visible. And you'll see why that is in a few minutes. But a fully visible type is made up of types that are completely known to us and can't be filled with some other type later. This is all we need in order to check that this impl is good to go. One important observation here is that any types after the first local type don't actually matter at all, according to the orphan rules. That means that we can put any type after bar at all, including type parameters, even though we weren't allowed to include those before bar in the order of the type parameters. So now let's talk about how this gets implemented in chalk. Well, the idea is that we create a new predicate called local impl allowed, which describes when a type is allowed to implement a trait under the orphan rules. Then we can go through each type, then we can go through each impl in our program and ask whether local impl allowed is provable for that impl. If it is, then we can move on. But if that isn't provable, we know that the orphan rules have been violated and that we need to produce an error. Here, the turtle type is local, so we know that we can implement display for it. But in the other example, a vector of turtles is not local to the current crate because vec is defined in the std crate. That means that we can't implement display for a vector of turtles according to the orphan rules. Okay, so how do we create local impl allowed? Well, more specifically, we need to ask, what are the lowering rules for local impl allowed? Like, how are we going to lower each trait that we come across in a Rust program? Well, we can figure this out by going through each case of the orphan rules. Let's say that we had this trait with two type parameters. We know, based on which crate the trait comes from, whether that trait is local or if that trait is upstream. If that trait is locally defined in the current crate, we generate a local impl allowed rule that allows any type to be implemented for that trait. This rule says that my trait is allowed to be implemented for any types at all. If the trait is upstream, we need to check those other conditions that we went over earlier. We need at least one local type, and for every type before it to be fully visible. The tricky thing here is that we need to somehow find the first local type. We can do that by taking advantage of the fact that during lowering, we know exactly how many type parameters there are in the trait. We can add one rule for every case of where the local type might end up. If any of these rules are satisfied, the impl is considered valid under the Orphan Rules. Now, these rules are basically an exact translation of the English sentence, find the first local type and make sure that each type before it is fully visible. The problem is that we actually haven't defined any of the main parts of that sentence, like when is the fully visible predicate actually provable? When is local provable? We aren't actually finished until we talk about is fully visible and is local. So let's start by talking about is fully visible. This one is pretty straightforward because we really just want to make sure that it isn't provable for types that aren't defined in some crate somewhere. We want it to be provable for all the types we can see, right? That's where visible comes from. But we don't want it to be provable for any of those type parameters. To do that, we can add a fact for every struct in every crate that uses the isFullyVisible predicate to indicate that it is a type that's fully visible. Since type parameters won't have any such fact, isFullyVisible won't be provable for those type parameters. We can make sure that isFullyVisible doesn't allow any type parameters at any level by making sure that we use if and checking that each type parameter of every structure is also fully visible in order for the structure to be fully visible itself. For isLocal, we just need to take every struct defined in the current crate and lower it into a fact using the isLocal predicate. In this case, we don't actually care about any of the type parameters that these types may have, because a type is local regardless of its type parameters. Notice that I've only added an isLocal fact for foo, because that's the only type in the current crate, and bar is an upstream type. So there's a couple of things that I've left out here. For example, I didn't cover how isLocal interacts with fundamental types. If you don't know what a fundamental type, you can absolutely come up to me afterwards and talk to me about this. And if you'd like to know more about any of this or how it works, you can also come and ask me about that. But all of this is actually fully implemented in Chalk right now. rustc doesn't actually use Chalk internally just yet, but you can expect that one day your Rust code might be checked with logical queries like the ones I've demonstrated today. The other part of coherence is the overlap check. This is currently an active area of research in my own work, and just like with the orphan check, my job is to figure out how to model this using logic. The tricky part about the orphan check is what I mentioned before. We need some way to model all possible compatible impls in the entire universe in order to make sure that you haven't overlapped with an impl that may be possible to define somewhere else. I have some ideas about this, but the research is still definitely ongoing. Well, thanks for listening to my talk. We talked about coherence, logic programming, and went over some examples of how we're using logic to model various parts of the Rust trait system. I definitely wouldn't have been able to do this without the help of a lot of great people, so I just wanted to take a moment to thank Nico, Boats, and the many other awesome people that have helped me figure all this out. Thank you. Here's my Twitter and a link to these slides, and I'll be around for questions as well.
Cool. So I really like the idea of using a logic language, or logic programming language to model this, and I'm curious if you feel like, let's say something violates these rules, does it seem feasible to determine, given a violation, turn it into a human readable explanation? Like if I want to understand, why my thing was or wasn't an orphan, and that could be some complex series of visibility rules and so on, like, is this something you'll have looked at, or does it seem feasible to provide some sort of translation layer from, given these rules were violated, turn that into something I could spit out of the compiler?
Yeah, so we actually already do this, right? So we have coherence checking already implemented in the Rust compiler. It's just not implemented using logic. It's implemented in Rust. And so we already produce error messages like that that give you a lot of details and tell you exactly what went wrong. So what will probably end up happening is with this implementation, you'll get enough information back to just know, like, oh, okay, this is what went wrong, and then we'll be able to produce the same or better error messages using that.
Quick follow-up. I guess I'm just trying to understand, like, say if you change the rules or added a new rule, like, to what extent is that process just done almost automatically by the fact of the design of your logic programming language, or is it like you would have to very carefully craft your error messages to each new change to your logic system?
No, I think it would work about the same as it does now. So you wouldn't have to necessarily change anything unless you change the orphan rules, right?
Thanks.
Yeah. Any other questions?
So I was looking at the coherence definition there, and I am extremely confused by why the is fully visible predicate only covers all types up to the locally found type. Is there some sort of arcane reason for that has to do with like what order type inference in this? I'd assume this already happens when type inference is all done. Like, why is that? Is that even necessary, really, or is this just?
Yeah, so I mentioned how these rules kind of seem pretty arbitrary and complex, and it's because they really do. Like, that's something that I personally had to grapple with a lot, and it's something I bugged Nico about a lot. But if you read through some of those blog posts that I talked about, they describe the reasoning behind the rules and why they work the way they do. And basically the goal is to ensure that every impl can only be implemented in one crate, right? And so we have to have some sort of local type there, because that way you have to use a type in your current crate in order to implement a trait, right? And then as for the ordering requirements, there's also some reasoning behind that goes towards that goal of only having one place to implement that trait for those types. Does that answer your question?
Not quite, but I guess I'll have to be satisfied with that for now, since it seems
You should
arcane.
definitely take a look at the resources that I linked to. They go in a lot of detail about this.
On the right and one, and type parameter on the left and the other, and they both match.
So while they explain that, any other questions, or do you have any more questions?
No, I'm good.
Okay.
So this is all nice, but like as a normal user of Rust,
Yeah.
I'm a very normal user of Rust. I don't know much. As a normal user of Rust, as a normal user of Rust who actually doesn't know Prolog, how does this impact me?
So this impacts you in a couple of ways. So the reason that we're talking about logic programming in general is because it gives us a lot of really cool benefits to the implementation of the trait system. So right now, and again, I don't know anything about the current implementation of the trait system, but what I've been told is that right now the current implementation of the trait system is sort of ad hoc, and it's random, it's all over the place. It's very difficult to debug or change or do anything to. And so the idea with this is that we sort of remove that entire layer and just have these logical rules that we can run in a very general logic programming engine and then solve. And so while you as a Rust user won't necessarily see the impact right away, because this is supposed to be a drop-in replacement, what it will do is it'll enable us to do cool things like really fast incremental compilation and all kinds of other things that will eventually benefit the users of the Rust compiler quite a bit.
I'm curious. You said that it was going to be a drop-in replacement. And what are the performance implications, if anything, if any? Will they be an
as far as I
improvement or
know,
an overhead?
as far as I know, we don't know yet, but it should be just as good. Otherwise, we wouldn't do it.
Perfect.
Yeah, we'll have to see. Any other questions? This one over there.
You described Chalk as a logic programming language, but you only talked about it in terms of implementing a type checker.
Yeah.
To what extent is Chalk a general purpose programming language with things like syntax and compilation versus just being a part of the Rust compiler? And is there any effort toward turning it into a general purpose language that anybody can use for any purpose?
Sorry, I should have clarified. Chalk itself is not a logic programming language. Chalk is based off of existing logic programming languages. It's an implementation of an engine that can solve certain queries within a logic programming language, and it's entirely catered towards Rust. So like Chalk has its own syntax, which we use just for testing. It's not actually used with Rust code. And it helps us write tests that sort of look like Rust code. And so you could say that the Chalk syntax looks like Rust code, but there really isn't any plans to make Chalk into a general purpose language or anything like that. It's just designed to be used to implement, to re-implement the trait system.
I've been brought into asking you whether or not this has any consequences in the realm of this magical thing we've been wanting for a very long time called associated type constructors, which may or may not have something to do with, yes, higher kinded types and the magical M word.
Are you talking about generic associated types and
Yes,
other things
yeah.
like that? Yeah, so yeah, for sure. Like Chalk already supports generic associated types. If you don't know what those are, don't worry about it. It already supports a lot of really cool extensions to the trait system. And the idea behind doing Chalk itself is that we can add these sorts of extensions really easily, right? Because it's just a couple more rules. It's a different set of lowering things, right? And so we can actually extend the trait system very easily and start to add these features faster if we have a more principled, well-reasoned implementation of the trait system. There's someone behind you.
So I've heard that in Prolog the search strategy for basically resolving predicates is actually fairly constrained by the specification because Prolog involves things like side effects and cuts and things like that.
Mm-hmm.
Do you know if Chalk Engine is somehow more flexible in the kind of search strategy you can use, if you can get any kind of optimizations from that?
So right now our solver isn't actually based off of a Prolog implementation. I think it started that way. There's a paper, I forget the exact title, it's in my backpack right there. I haven't read it, but it's in my backpack right there. And it talks about something called hereditary Harop formulas. And so there's a paper, it's called a proof procedure for hereditary Harop formulas. And so we use a modified implementation of that. So we probably don't have some of the downsides of a regular Prolog solver because we're not using Prolog directly. But there are other limitations, like a lot of the research that I have to do next has to do with the impact of negative reasoning, like negating a query, putting not in front of it, and what that does, like what impact that has on the solver and what it can solve.
Cool, thank you.
Any other questions? Okay, one more. Last one? Or?
Yeah, sure, take one.
Okay. Can somebody pass along the mic to over there?
So there's currently also an effort to reformulate the borrow checker in terms of logic programming. Based on what I've seen, it seems like the data log engine that it's using is a less powerful form of logic than what Chalk is using. Mm-hmm. But what's the relationship between those two efforts?
I have no idea. But so I've read the blog posts that Nico put out. But Nico would definitely be the right person to ask about that stuff. Anyone else? Okay, thank you very much.
Next up, we have Raph. Raph works at Google on Fuchsia and has written stuff like Xi and a whole bunch of cool things, and is talking about GUI in Rust. Here we go.
Thanks, Manish. All right, let's get plugged in here. It's working. Yes. And then I'll hit present. Great. Fantastic. Okay, great. So I'm going to be talking about kind of an exploration, like kind of asking this question of, like, can you reasonably write GUI code in Rust? Like, where are the challenges? Where is it hard? And so just kind of as an outline of this talk, so first of all, I should say that this is my 20% kind of personal project. This is not an official Google product. And any opinions expressed are also not official Google policy. Great, so there's kind of a lot of material here. So I'm going to just start talking a little bit about, what makes GUI programming different or special compared with just regular types of programming that you might do, and what are the specific things that I'm trying to, get into, and especially like one of the themes is performance. This is kind of the niche that I feel like one of the things that we don't have as much as we'd like in kind of GUI toolkits is performance, and I feel like this is an opportunity to do something that goes a little bit beyond, a little bit better than what's out there now. And then there's one specific piece of this. So, Flutter is a very interesting kind of new GUI toolkit, and I think there's a lot to learn in there, a lot of good pieces. One of the pieces that I think is most interesting and can be like generalized to other systems is the layout protocol. So I'm going to that's kind of going to be the case study of like, how do we do the Flutter layout protocol in a smooth way in Rust? So doing it in just object-oriented techniques, if you just try and write your object-oriented code in Rust, it's not going to go well. And an alternative to that is a data-oriented approach, and I'm going to go into quite a bit more detail about that. And then kind of the latter part of the talk really is a workshop in like, how do you use specific techniques to write Rust programs in a kind of a more natural, intuitive way. So what am I trying to do here? So I'm trying to do, this is all really motivated. There's an experimental Windows front end for Xi Editor. So there's the Mac front end, there's a good GTK front end that exists, there's the Fuchsia front end, which we're also working on, but there's nothing that's really good for Windows. So I was like, okay, let's go in and try and do that. And there's features that I want. So I don't want it to look like a cross-platform app, I want it to look like a Windows app. I want performance, performance, performance. So there's actually a lot of stuff in here. Latency, energy usage, startup time, smooth scrolling. These are all actually kind of difficult problems. I'm not going to go into a lot of detail on these tonight. That would be another talk. But the consequence of wanting to solve these performance problems is I can't really use existing abstractions very well. I am pushed towards using WinAPI calls and be able to control what happens at a very low level of the system. And then another goal of the work is that I want this thing to be very easily usable from Rust. So if I have a GUI program, then it would be great if I could just type cargo run and there's no like complicated like management of non-Rust dependencies or anything like that. It should just build an executable that will be a GUI app. So doing a GUI toolkit is a fairly ambitious project. And in order to make it practical as a sort of a side project, that means that there's a lot of problems that I have to explicitly choose not to solve. And so here are some of the things that are out of scope of this work. I am not doing cross-platform GUI toolkit. And again, cross-platform would really make this work a lot harder because I'd have to find, like, you really run into this problem of lowest common denominator, of really not being able to address, like, maybe the best way of doing, let's say, swap chain presentation, right? So I'm explicitly putting that out of scope, and I'm trying to learn what I can from doing a GUI toolkit on one specific platform, which is in this case Windows. I'm not trying to solve GUI for all possible apps. I'm really like just making a GUI for Xi Editor. One of the really interesting like directions of GUI toolkits, especially in the last maybe 2, 3, 4 years, are these reactive APIs where it looks like a functional program. Those are cool. I am not doing that. I am doing a kind of a traditional widget tree. And then it might be interesting future work of, can you layer a reactive interface on top of a widget tree? And I think that would be really interesting work for somebody, not me, to do. And then also, just kind of emphasize, like, at the moment, this is experimental, and this is kind of a toy toolkit. I'm not doing internationalization. I'm not doing accessibility. I'd like to have a structure that makes those things possible. Like, I don't like, for it to become really real, those problems need to be solved, but I'm not doing that today. So I wanted to go through like some of the alternatives that I considered. Like I've kind of motivated a little bit why I want to do it myself, but there are other ways that you could do this. You could take an existing toolkit like GTK or Qt. Those are kind of the two of the main ones that might run on Windows. And they're not fully satisfying. So definitely my concern about performance basically means there's nothing out there that really performs exactly the way that I want it to. And then certainly another big challenge of using these toolkits is that when you're programming to them, the API doesn't feel like Rust. You're kind of in a different world where you've got objects that you're manipulating, and there's an interface that you're aware of. And then they also don't really necessarily look like Windows native. I mean, Qt actually is pretty good. And you can make GTK look good, but it's still, like, now there's 2 layers of impedance mismatch. I'm programming to something that's not Rust native, and then it's displaying to the end user as something that's not fully Windows native. Immediate mode GUI is something that I looked at. There's a couple of different ways to do immediate mode GUI. There's a Rust bindings for dir imGUI, or you could just write it. It's pretty simple code. And I think that's an interesting thing to explore. It wasn't exactly what I wanted to do because it's really difficult to like propagate small deltas through an immediate mode GUI. And that's really the whole thing about Xi, that when you press a key, everything that kind of flows through this pipeline is a little bit of a delta, and you just only want to do the work for that delta. You don't want to like repaint the whole world. And generally in an immediate mode GUI, you end up repainting the whole world. There are some existing Rust frameworks that I looked at. There's Piston, which, really Piston is also, I think at this point, kind of experimental, speculative, and the features that it has are just not quite what I need for text editing. And when I was experimenting with it, I was also finding the performance in its current state was not what I wanted. So I felt like this was an opportunity to try different things. And there's also Realm, which is, I think, an example that is actually addressing a higher level of the stack. The current implementation of Realm is a wrapper on top of GTK-RS, providing this kind of reactive interface. So that wasn't really going to solve my problems either. So let's look a bit more deeply into like, how do you program a GUI? How do you program? You want to display a window, you want to display widgets in that window and have behaviors and so on and so forth. So you have these components, and so you've got like a lot of components, and they're interacting with each other, so they're kind of they're coupled. The components themselves are very stateful, so that kind of pushes you in a particular direction. And then the components themselves are dynamic. Like you might press a button and it causes a tab to pop up or something like that. So you've kind of got this combination of stateful, coupled, dynamic things, which a lot of people might look at that and say, this is a hard place for Rust to be. So in the traditional object-oriented world, each one of these components is an object. And then those objects live in an inheritance hierarchy. So in the case of GUI programming, you've got like maybe something called view, which is the base of this hierarchy, and then things derive from that, and then you might have, it might be a very rich hierarchy because you might say, okay, one type of component is a container that contains other components, and then all of your containers, like your rows and columns and scroll views and stuff like that, derive from that. So you've got this very inheritance-based like hierarchy. And then you certainly, in a traditional GUI, you don't have to do this, but in a traditional GUI, you generally put the objects themselves at runtime in a tree hierarchy, a containment hierarchy. which is different than the inheritance hierarchy. So there's kind of two hierarchy concepts. And then again, in a traditional object-oriented world, you've got references all over the place. Like all of the containers, they don't, you could say they own their children, but there's not really a distinction between, an own reference or any other kind of reference. It's just a reference. And then the same for your parent. You have a reference up to your parent. And again, in the traditional object-oriented world, they didn't really come from a place of thinking about, whether something is mutable or not, kind of controlling access to mutable state. So you kind of have this model where all of the objects that are making up your GUI are available to be called by any other object that has a reference to it at any time, and then that might very likely to cause a mutation or something like that. And you can actually do kind of crazy things, like let's say that you're traversing this hierarchy and you need to paint, and then in the middle of the paint call you say, all right, I'm going to insert something. I'm actually going to mutate my widget graph at the time that I'm painting. And if you're in C++, well, you just caused iterator invalidation, and that that causes things to blow up in a very pretty way. If you're in Java, then it just means that something is going to happen. It's probably not going to be a undefined behavior, but it might very easily violate kind of assumptions or invariants. And there's nothing that really prevents you from doing these strange things. There's no enforcement of kind of expectations. And I worked on Android UI Toolkit for several years, and I was very impressed how creative developers could be in coming up with ways to explore that space. So can you program using this traditional? I mean, we have a lot of knowledge. We know how to build GUIs in this kind of traditional object-oriented model. It really kind of grew up hand in hand with the evolution of Smalltalk and other languages. Can we just take those patterns and program them in Rust? And the short answer is yes, but you just don't want to do that. So you've got a lot of things that Rust does not support well. So the first is inheritance. And Rust does not do inheritance. It doesn't have like a class and a kind of the traditional inheritance model. You can fake it. There's actually tricks that you can use, like using deref. I won't go into too much detail because this is really a talk about what you want to do rather than what you don't want to do. I think a bigger problem in inheritance is that you end up, when you have this graph structure, when you've got a widget and it's got a parent and it's got children, how do you represent those references? You need to have those references because you're going to be doing things like propagating. Like you might, if you have an invalidation, you'll be bubbling that up the tree, and then there's other things you're doing that are going down the tree. And so you need those references. You need to be able to traverse that graph structure. How do you represent that? And the kind of escape hatch that Rust gives you in this case is interior mutability. So this allows you to say there's a ref cell, and you can have many. So there's ref cell, which allows you to get immutable access to that, and then there's a reference count, which is either going to be a weak reference or a strong reference. And the reason you do this is you say, okay, I basically own my children. That's a strong reference. But when I have a reference to my parent, if that was also a strong reference, I'd have a cycle, and that would actually mean that I have a memory leak. So using a weak reference for that breaks that cycle, avoids the memory leak. So you can do this. I've actually written a fair amount of code using this model, but it is not fun. It is pretty painful. So you get a lot of extra noise in the program where you're constantly borrowing these explicit references. The types get, you get a lot of angle brackets, in a row, which is not great to look at. And it's also not fun at runtime because, you need to borrow in order to actually be able to do anything with these objects. And if your borrow is too long and you do something while you're still holding the borrow, then you get a panic. Or in the case of multi-threaded programming, you get I've kind of written this in the single-threaded case. And that's actually another problem. It kind of forces you to choose, am I in a single-threaded world or am I in a multi-threaded world? In a multi-threaded world, you'd get a deadlock, which is also not a great experience. So I think we want to look at alternatives. Like, don't just write object-oriented code in Rust. How else might you structure a system? And so there's, from the kind of game world, mostly C++ programmers, there's been a lot of really interesting work in this space. And I think the general term, which I've adopted for the work that I've done, is data-oriented programming, of saying it's not object, you're not factoring everything into objects, but you're looking at the data and you're trying to say, how do I program using this data? And a specific thing that's been getting a lot of attention lately that was really inspiration for this exploration is this thing called the entity component system architecture. So to kind of break that down, an entity is a reference to a component. So it's usually implemented just as a number, a usize. It's effectively an index into a vector that's holding the components. And then sometimes it's a little bit more sophisticated. It can have a generation so that, if you delete it and you've got a stale reference, that you can actually detect that rather than just accessing the wrong component. So the next piece, entity component system, is component. And that's your state. So these components have to be stateful. They have to represent, like, did the user hover their mouse over it? Was I just clicked? That's state. And in the entity component system, you really represent state in the simplest possible way of saying, each component has some state. It's just bytes. And then it's up to the rest of the system to decide how to interpret that state. And then the behavior is entirely encoded in these systems. So there's one system for each type of behavior. And so if you have like a button, that might have several behaviors. So you might have a lot of systems that, that implement that behavior. And so kind of the way that you can think of the system running is that in a kind of a continuous loop, like so you're kind of always updating these systems, you run the system for all of the components that might be interacting. And then in a simple implementation, that might just be a brute force loop over everything in the world. Sometimes you might do a more sophisticated filtering so that you say, okay, the mouse is here, it's only going to interact with this, and that's more complicated. But you can kind of have this model that there's just kind of this continuous, you're always invoking the systems. So this is really getting a lot of attention in the gaming world, implementations in C++. People are interested in it because it really solves a lot of problems of both efficient implementation. These things tend to be a lot faster, and that they're kind of the coupling that you get allows you to change things more flexibly, people are finding. So there is a Rust crate. This is not what I'm doing, but it is an interesting exploration, and I kind of encourage other people to play with this and experiment with like a pure entity component system. And there are crates out there that will help you do this, like Specs. And one of the other things that Specs does that's interesting is that it allows you to run your systems in parallel and exploit multi-threads, which is a really interesting direction. So as I said, I'm not doing a pure entity component system architecture. I'm doing something that was inspired by it, but I think the right way you want to think about this is that it's a hybrid. It is using concepts from data-oriented programming, and it's doing other things that are actually pretty traditional, pretty familiar to anybody who's built one of these GUI toolkits or used one of these GUI toolkits. So I'm going to kind of walk through the actual implementation, the actual struct that implements UI state in this case. And the first thing that you'll notice is that I've got a structure of arrays architecture. In an object-oriented world, all of the state for a widget is in that widget. So you've got the widget-specific behavior, you've got the references to children and parent, you've got other things like geometry, all of that is kind of encapsulated in one object, and then you have a whole bunch of those. And kind of one of the central principles, or one of the big tools from the data-oriented programming world, is that you don't do that. You do structure of arrays so that you have all of the related data in, in its own structure, and then you have an array, so you've got one instance of that structure for every component in the system. So I've got that. So I've got these vecs that are blue that are all kind of parallel. So the same ID, which is just a usize, that's used as a handle to reference one of these components, is an index into any one of these arrays. So let's go into the what arrays do I have? What state am I representing? So the first one, kind of the central one, is widgets as a vector of box of dyn widget. So Dyn widget is a trait. I'll go into a little bit more detail, but just think of that as having your behavior so that, it tells how to paint, how to lay out, how to handle mouse input. And then each type of widget has its own impl of widget trait. And of course it's Dyn widget because, I want to be all up to date and with it. Actually, the code is still box widget, but, future work. So that's the behavior that is specific to the widget, to that particular widget. So then I have the graph structure, which I mentioned. I kind of gave the example of what does that look like in the kind of interior immutability world. In this world, it's pretty simple. You have these arrays that just hold the graph structure, and one of them is just a vector of children for each node, and then each node also has an ID that just references its parent. So there's no complicated ownership or borrowing. You're not fighting the borrow checker. That's really a theme, that if you're trying to program object-oriented programming in Rust, you will be fighting the borrow checker. And in this kind of data-oriented world, you're not doing that. So then I also have other state per widget. I have geometry, which is pretty much just the size, location and size of the widget. And then I have these listeners, which I will be talking about in considerably more detail later. So this decision to represent like the core widget state in this box, this vec of box of Dyn widget, this is kind of the central architectural decision that everything kind of flows from. The rest of the design really flows from that choice. So, when you want to reference a widget, you just have the index into this vec, which is usize. You've got the widget trait, which has this widget-specific behavior. That is only the widget-specific state, though. So if the other state, like geometry and the tree and stuff like that, that's actually held by the system. And then you've also got this kind of principle that when you're traversing, when you're actually doing the work of the GUI, you're going through this vec and you're borrowing a single widget, and you've got a single mutable reference to that widget, and only one of them at a time. So that is a little bit of a challenge. Like if two widgets need to interact now, like if I press this button and it causes this, other thing to change, how do we express that interaction? Mystery. Which I will get back to. But before I do, I want to go into this detail. Like one of the really challenging things that any GUI toolkit has to deal with is layout. And in a kind of any modern GUI toolkit, you want to do layout in this responsive way so that if, for example, you're dynamically resizing a window, there's all kinds of things that might want to happen as a result of that. Like, for example, you might want to go from a one-pane to a two-pane layout. And so that concept of like a break, which is not continuous, is a test of how expressive is your layout system. That there's like a lot of interest in things like cassowary, which is a sort of a linear constraint solver, and it's kind of difficult to express those things. It's easy to express kind of a smooth, like as it resizes, you have more space in proportionally given to different widgets, but it's very difficult to do things like that, those breaks, or if you have like wrapping, if you've got like text, or if you've got like a series of buttons or something like that, and then you expand, it might go from needing 2 lines to 1. So you want to be able to express those, patterns, that kind of responsiveness to size. And Flutter has a really interesting way of doing this, which allows you to express those, and is really, really, really efficient in his simple programming, and kind of like satisfying all those constraints at the same time is fairly impressive. So the way that it works is that you go through the tree, and you pass a constraint down, and then you traverse down into the tree, and then what flows back up is just size. This is how big, how wide, and how tall each widget needs to be. And the constraint, there's a little bit more complexity to it with inherent size, but the guts of it is just what's on this slide, that the constraint is just a minimum and a maximum for width and height. And so the size that comes back up has to be somewhere between minimum and maximum. And that's basically all there is to it. So then you do a one-pass traversal of the widget tree. So when you do this traversal, when you're laying out your system, you only touch each widget once. And that is a huge principle. Like if you look at Android, Android has relative layout. It's not really recommended for exactly this reason, but if you have nested relative layout in Android, that's an exponential increase in the number of times that you're going to touch, that you're going to call a layout method. So the difference between linear and exponential kind of matters. So it would be nice if you could do like a really simple traversal. Like for example, when you're painting, you can just say, just go through the tree and paint all of your widgets. For doing layout using this Flutter protocol is not quite that simple because the order of the traversal is dynamic, and I'll go into that in a little bit more detail in the next slide. But first of all, if you're interested in this and also other details about how to build the guts of a widget system of a GUI toolkit, I really recommend this video, Flutter's rendering pipeline from a couple of years ago at Google I/O, Adam Barth. And it is very dense. It has a lot of good stuff in it, including a lot more detail about this layout protocol. So why is the traversal why is the order of traversal dynamic? So if we go into a little bit more detail into a row or a column, that it roughly looks like this. That you've got children that are both non-flexible and flexible. Like if you think about a bar that has like buttons and then maybe like a text field, then maybe your buttons are not flexible, but your text field is flexible. So the algorithm basically says, do your non-flexible children first. Go to each of your non-flexible children. Don't give them a bound. Let them tell you any width they want. Then you get those widths, and then you just compute, well, how much space do I have left over? Like I've got this width, the non-flexible children have these widths, this width is left over, and then you go and you proportion those out to your flexible children. So it depends which children are flexible and which children are not flexible, and that might be dynamic. So that needs to control the traversal that you do your non-flexible children first. So the other thing I think to notice here is that this is kind of the way the code looks in Flutter, and you do these recursive calls. And you can immediately see that in this model where you've got like a vec of widgets, and then you take a mutable reference from that vec to just the widget that you're calling layout on, and then if that widget wants to do a recursive call on some other widget, it needs to get a mutable reference, which it's going to borrow from the immutable reference of the vec of widgets, and you're stuck. You can't do this. How do we fix that? So in the data-oriented world, there's tricks. And I think maybe trick it would be better to say this is a pattern, right? And so you see this pattern in things like iterator and in future, where you have a computation and you don't want to do the entire computation in one gulp. You don't want to say, I'm going to call you, and then you're going to do your work, and then when you return, your computation is done. You want to break it out so that there's some way where you can say, I'm going to call you, and then you're going to do some of the work, and then you're going to return something to me, and then I'm going to call you again, and that is going to resume the work that was suspended. And by kind of these repeated calls, we're going to get the job done. So to kind of adapt that idea or that pattern to the Flutter layout protocol, what we're going to do is we're going to have this. This is pretty much the signature of this method in the code, where we're going to call the method with a mute self, so that it can can access all of its own state and do anything it wants with it, including mutate. We're going to pass in the constraints, which are just same as the Flutter code. We're going to tell it what its children are, and notice that that's a non-mutable borrow. You don't want to be able to, so that's encoded in the type. All right, and then what we're going to do is that we're going to pass this option size, which is basically the result of the last of the last widget that's the child, right? So when this widget returns, it's going to either return the size and say, I'm done, here's my size, we're laid out now, or it's going to say, don't know yet, but please request the layout of this child and then call me again when you get the answer to that. and then you're passing down or you're passing to the child, what are my constraints for that child? And so there's this kind of flow of data. So it's really of a flow of data rather than a flow of control instead of a recursive call down the call stack. I think I have a picture of that. Yeah. So in the kind of object-oriented world, you're kind of going deeper and deeper down the call stack with control flow. And in this kind of data-oriented world, you've got this data flow where your system is just repeatedly calling layout on one object at a time in your box of a vector of widgets, and then you've got this data flow that when you request, oh, please lay out my child, then you've got the data that comes back up from that call into the next call, and that implements this layout protocol without fighting the borrow checker at all. There's no interior immutability. There's no anything that's kind of difficult or painful to program. So another way of looking at this actually that's kind of interesting is that if you have like a really simple recursive program, like, if you think about factorial as a recursive program and you don't want your call stacks to be deep, there's kind of this transformation of how do you make that into an iterative program. And that really is pretty similar. I think that's the same idea, that you could maybe think of that not just as a special one-off hack, but as a general transformation that you can do to get your algorithms into this structure. So that's kind of like when I'm talking about like programming techniques for how do you implement these patterns in Rust. That's the first. The second that I'm going to talk about is state splitting. And so state splitting, or this is just what I'm calling it. And so when you think about like different parts of the system, that you have different needs of what needs to be mutable and what needs to be immutable. So when you're doing layout, which we just went into in some detail, you need a mutable borrow of the widgets because you want them to be able to do whatever access to their own data. You need to mutably borrow the geometry because you need to store it somewhere. And then you need to traverse the graph. And that should be an immutable borrow because you want to be able to say like for child in this widget's children. And while you're in the process of traversing that, that needs to be an immutable borrow. You do not want anything mutating that at the same time. There's something else you might be doing where you're going to have a different, different pattern of what needs to be mutable and what needs to not be mutable. For example, if you're doing something like, you press a button and it causes a panel to pop up. Well, popping up the panel means now you need to be able to mutate the widget graph. So, depending on exactly what you're doing, you have a different pattern of which pieces of that state need to be mutable and which pieces of that state need not to be mutable. And the way this is implemented is actually kind of simple. And this is one of the reasons why it has to be structure of arrays rather than array of structures. Because structure of arrays allows you to borrow each one of those arrays with a different reference with different mutability. So when you're doing layout, then you borrow widgets and geometry with mutable references, and you borrow the graph with an immutable reference. And for the other recursions, other traversals, you have different patterns there. And Rust helps you do this. It makes it really easy if what you're taking that reference from is self. So if you've got self, then you can kind of take references from the pieces of self, from the fields of the self struct, whereas if, for example, you were handed just an and mute reference to the thing, then it's a lot harder to do that state splitting. You get, your compiler will complain. So this is just a pattern where you're not fighting the borrow checker, not fighting the compiler, that you take those references, and then as you do the traversal, like in this case, you've got these kind of three main references. As you do the traversal, you traverse those down. So the other thing, like for example, if you look at this slide, that one of the fields that I didn't talk about yet is this layout context. And so that's another important piece of the state splitting concept, that context lets you do things. And in the case of layout, it doesn't let you do a whole lot. Maybe it allows you to query the geometry of other widgets in the tree. So layout context is not a very powerful context. But there are other contexts where you want to be able to do more things. And so the idea is that that context has that kind of encapsulates the mutable reference that let you do the actions that are desired at that point. And that is writing, like, what can you do? Like, can I mutate the graph? Can I query, a geometry of a child? Can I send an event? Those are methods that are on the context. So you're writing into the type of these methods. What can you do and what can't you do? And so that's a static compile time enforcement of the invariants. For example, can't mutate the widget graph while painting. The context that's passed into the paint method does not have a mutate widget graph method on it. So you don't get to have as much fun at runtime. So the last part of the design really focuses around this listener concept. And again, so we kind of talked about, like, how do you break the state down into these components? How do you do these things like, pane and layout? But you get these interactions. These are coupled, like different pieces of the world are interacting with other pieces of the world. And one of the things that you wouldn't be able to do, like if you press a button, is just call the update state method on like a text field or something like that. So the way you need to encode these interactions, you need to be able to express these interactions. And the way I do it in my code base is that your context for these handler methods basically lets you put events in a queue. And so you're queuing events that are going to be sent to generally other widgets in the tree. And so the way I do this, so you've got this coupling, right? You've got this dynamic coupling. Like, what's an event? And so I'm going to reach into the toolbox of loose coupling tools in Rust. And one of the ones that you see not that often is any. And like, I don't want to overly constrain. Like, you might have an extremely simple event. Like, if you've got a button, then an event might be just like, set it to pressed or not pressed, right? So the actual state content of that might be a bool. But then I might have a very complicated widget, like a text field, and it might have some very advanced structure that's saying exactly what do I want to do to update the text field in this text widget. So box any pretty much lets me use whatever structure I want, and I just put it in a box, and then I put it into that queue, and then when the handlers return, so the handlers are invoked when you have some kind of input, like a mouse or a key or whatever. And so you run the handlers, and you give them a context which lets them put the events into these queues, and when that's all done, then you run the queues. And running the queue is basically just calling the dispatch into the listener for each of those widgets. So you kind of have this, it's almost like a bipartite graph where you've got the widget, which expresses really kind of view and behavior to input. And then you've got the listener, which is an object that lets you encode, I think, application state. So maybe in a, kind of traditional lingo, you might call it a controller. And then the listener is given a context that lets it do a lot of stuff. So it can interact with widgets. That interaction with widgets is synchronous, so you can do both sending commands and querying and getting data out of the widgets. And then you can do other things like mutate the widget graph, and kind of express this sort of complex interactions in your app. So again, like the idea here from maybe what is a general lesson that you can do in building these systems is that you've got these tools for loose coupling, both in the data and in the control. So you're not doing control flow, you're not calling methods, you're sending data across. And then you've got this box any, which is like this kind of very interesting way of getting much looser coupling from the different components of the system. So that's kind of, the structure that I wanted to, just kind of report on the explorations that I'm doing, and very happy to take questions. The code is here, Zywin, and you can, I think, let me see if I can take a chance here and just run it a little bit. So I'm not going to compile it. It would take about half a minute to compile, but I did it earlier just to show there's no interesting dependencies. So there's a calculator app, and, it's not that interesting. I've done almost no work on like the styling, so I'm not even showing like highlights as you mouse over yet. But one of the things that's really cool is, sorry about that, is this dynamic resizing. And I don't know if you see it on these monitors, but there's like a real 60 frame a second, and then it's like sticking to the resize cursor when you do that, which it turns out is really difficult in Windows. It's kind of surprising how hard it is to do that. So I researched that so you didn't have to. And then this is very experimental, but this is the editor itself, and it works. It has very basic functionality. You can select and stuff like that. It's still very much work in progress, but I just wanted to show that that this is actually kind of in the process of becoming hopefully a real app. So now I'd like to open it up for questions. Oh.
Okay, I have so many questions, so I'll just ask. I also have Manish, how many I can ask?
Like one first?
One.
We can, like,
one. Oh, no, I have to choose. So you said you were going for the native look and feel.
Yes.
How do you kind of marry this system that you've built with like the Windows APIs that like actually like do the standard drawing and like the components and things like that?
Right, that's a good question. So in the case of things like drawing the menus, and the file dialog, which are really important, it's pretty straightforward. I just call them. They're just Win API methods that are available, and I call those. And those are not tightly integrated with this kind of widget like display mechanism. So one of the things that I am not doing is embedding the Windows common controls. I'm kind of taking control over the way that the application surface is being drawn. So in that case, it's just like taking care to draw the application surface in a way that's consistent with the Windows style.
So it seemed like the API you presented for the widget seemed very naturally expressible as a coroutine. Like you explicitly reified the state as this layout result, but I guess I was wondering if you had any plan. I don't know if it's actually on the nightlies yet or not, but like do you actually have any plans to try and use like the explicit coroutine API? Because also like I only saw like that most recent post or whatever. I don't know, for example, if like having a pinned self would like fit with your borrowing model. Yeah, I guess I'm curious if you have any thoughts on the usage of coroutines to try and model your widget painting function.
It's a really interesting question. So like I think painting actually is not hard. Painting is just straightforward code.
Yeah.
But layout is slightly difficult. And I thought about that when I looked at it. This idea of like how do I transform like what I would express as sort of a call where I want to like kind of express this as straight line code. The simple fact of the matter is that it's not that much worse the way it is, just doing it the simple way, than it would be if you implement it. You kind of have to do the same things. You have to kind of keep track of where you are in the iteration. So I think it's an interesting question, but I wasn't thinking to myself, wow, this code would be so much clearer and nicer if I had access to coroutines.
Yeah, so I guess, how do you deal with errors, if that makes sense? So like, because the system is so highly decoupled, a lot of the time, like if I get an exception in my Java program because I'm doing something silly, like trying to do IO in the UI thread and like try and grab an image from GitHub and it fails or whatever, like I'm doing that somewhere else in this system. So how do you track that failure all the way through to where it actually turns into a hard error in the like paint method or whatever?
That's a really good question. At the moment, I don't have any real error handling in the code. I did promise that it would be a toy UI, and that's definitely one of the things that distinguishes toy from production systems. But I think it is a good question. It's potentially kind of complicated because, like, if something is happening because it got sent an event, and if the error is actually inherent in the event it got sent, then you have this thing of like, how do you attribute? How do you know where that came from, right? And I don't have an answer for that. That's actually a very fundamental thing. Like anytime you build these asynchronous pipelines, you have to deal with that. And when you have that tall call stack, at least you have that context. And then I'm saying, well, I'm getting rid of that tall call stack. But I don't know. I mean, so far, like as I say, I'm kind of trying to do a very specific thing where, I'm really just trying to build an editor. And I think I'll probably end up with basically a lot of these methods, like these methods return, like you saw that kind of enum that's either, like in the case of layout, it's like size or request child. And it could easily be size, request child, or error. It could just be a result of that. And I'll probably just do that and then have kind of patterns where if the error is inherent in the input, then I wrap that in the result. But it's a good question, and be interesting to see how that actually works out when it's kind of more baked.
This might be too big of a question, but like the big user interface in Rust is servo. And so I was wondering, I'm not sure if you can briefly compare and contrast like the kind of techniques that servo is doing for parallel layout and styling and layout to this approach.
Yeah. I am. I probably should have put servo in that kind of alternatives, slide. And I'm not deeply familiar with, the kind of advanced technologies that servo is doing. There's definitely a feeling of a lot of what servo, this is my interpretation, a lot of the kind of very fancy stuff in servo is to deal with web content, which has a lot of sort of nasty, unpredictable aspects to it. Like you might have a ton of overdraw, or it might have kind of complex clipping or something like that, that requires this parallel layout to work. What I'm doing, once I get access to that really low level, I might be doing sophisticated things in the text plane. Like I might be doing, really fine-grained calculation of deltas, but nothing is really complicated. So I'm finding that like if I just call if I like break it down so I'm doing the minimal amount of work and just calling the Win API things to draw, that I'm getting what I need. And so it feels like maybe that's one thing of like less complexity. You brought up parallelism, and that was one of my prepared slides, which is that in the existing code base, everything is single-threaded. But it's really interesting when you look at these, when you look at the design, you see opportunities like maybe I could call the layout of my children in parallel. That the widget, in the widget trait that it has to represent to do layout, it's just an and mute self. It doesn't need to have like this like entire world mutable state. If you make that layout context really, really tiny, then you can call all of them in parallel. So I think that there is actually a lot of potential to do that kind of thing.
In your slides, you had type ID equals usize.
Yeah.
Is that how it is in your production code, or do you do something to make that a little bit less error prone?
At the moment, it is just that. And I think I'll see how that goes. In the ECS world, you usually put some kind of or some kind of extra thing to make it, so that you're much more likely to catch because there's nothing that enforces that ID has to be valid. And so, like having some additional runtime checking is useful. So far, I haven't needed it, but
have you hit any bugs?
Well, I mean, there's always bugs, but
related to the specifically
no,
related
I haven't.
to the
I haven't
ID
hit,
mixing.
I have not hit ID bugs yet. No.
Do you compact the vector of objects when you remove an object? Do you remove objects?
Right now, the code doesn't have object removal, but that is one of the things that needs to happen. I mean, you're constantly, this will be a long-running session where you will be doing things like popping up, dialogues and so on and so forth. So that needs to happen. I think it's very likely that you will not need to compact that vector. I don't, it's because basically, if you think about it, the size of that vector really represents the high water mark of the number of objects that are active at one time. And that seems pretty manageable. That seems pretty small. There's a small amount of additional work that needs to happen to make removal work reliably. And like one of the things I kind of left out is that you want to have a method call on a container that says on child removed, essentially. And then you want to give that container the option, if it has any state that is specific to that child, the guarantee is like nothing is valid after on child removed, for that child. And so it should forget anything having to do with that child's ID. Does that answer?
Yes.
Thanks. Other questions?
Have you given thought, so like you're avoiding inheritance, which is phenomenal, and you've got this single widget trait. Traits like look a lot like static mix-ins, but there's not much of an affordance for like specializing these things in the system you described. Have you given much thought to how you would do that with this kind of system?
How I would do...
Like you talk about like having on-child removed.
Yeah.
But you presumably have elements of the system that you don't want to force all widgets to implement.
Oh, see what you're saying. Yeah. Right now I have a very simple thing where pretty much all of the methods on widget have a default implementation, which is to do nothing. And that's working pretty well for me. I actually think it's unlikely that I'll run into a case where I want to do anything more fancy or complex. But, you can imagine, like, it's kind of a function of, well, how many methods do I expect having on a widget? Right now, it's like a half a dozen. By the time I'm done, I expect it'll be probably 24, maybe. And so if it was going to get...
which you don't expect people to have to implement.
Right, exactly. Most of which would have default implementations. Most of them would be kind of specialized. And then, you're going to have a lot more for doing things like accessibility and so on and so forth. But, I don't think that... I think that's just kind of at the threshold. Like, if you look at mature widget systems, it's not uncommon for there to be 100 methods or more on a, view base. And then you might really look at, well, how can I organize this so that I don't have like this huge V table for every object? But I don't think I'm quite where I need that yet.
As just a small follow-up, I looked at a few of like the ECSs for like doing game programming, and there is exploration in like doing more generic things. So you could have a table of like all your buttons that like also has another table that like, this is all the widgets. And then, so you could like dynamically grow and rather than like having, one big meta widget, you could have like thousands of these other things that may or may not implement your interfaces.
Yeah, and again, I really I'm kind of excited about the possibility. Like, I kind of would love to see somebody explore a more pure, more data-oriented, like strictly non-dynamic dispatch approach to this problem, and then compare and learn, like which is actually a more natural exploration of the patterns, expression of the patterns.
So from the sound of it, you're not really using the Win32 components. You're not really that coupled to Windows. What? How? Okay.
Yeah. So this is something that I've been thinking about a little bit, and the reason why I chose Windows, aside from the fact that we need Windows client for XiEditor, is that Windows has this nice property that what you need is provided by the system, and that's the 2D graphics abstraction and especially the text abstraction. Making something that can just draw rectangles and strokes and stuff like that is not a very complex API, but an API that handles text is complex. And so when I was writing kind of directly for Windows, there's a solution to this, which is you just use Direct2D and you just use DirectWrite, and then your text rendering, font selection, emoji, all of that works just like just like the platform. If you're doing something else, like a lot of these, Servo is no exception. That if you're doing Servo web render, then you need like some other technology there to do the, especially the text. So the way that I would like to see this happen is I would like to see, this is kind of a wish list really, that I would love to see a 2D graphics abstraction that has methods for draw a rectangle, clip to this path, whatever. This has kind of been known since the days of PostScript what these APIs look like. And I think that there's a real opportunity in the Rust ecosystem to build this thing so that then it can be implemented with like a bunch of backends. And of course you would have like, Direct 2D as one of the backends, and you'd have almost certainly like WebRender as a backend. And you can imagine like maybe, half a dozen things that would be useful, like maybe, just generate PDFs if that's what you're trying to do. So yeah, the code is structured in layers. And so the goal is that there's this lowest layer, which I call Win Shell, which is hopefully where all of the unsafe code lives, which is the kind of, like interacting with the Win32 message loop and message pump and, all that kind of stuff. And then there's the Win UI layer, which is really what I'm talking about today. And then the layer on top of that is Win itself. It's the editor app, which then the idea is like there could be other apps that use this toolkit, maybe not, but the layering is to encourage that. So the idea is you kind of make, like right now Win Shell is a very thin wrapper. It's like in most cases, it's just safe wrappers around Win32, Win API functions. And you could just totally imagine, having a cross-platform implementation of that layer that the layers above would be able to use. So it's something I'm thinking about, but I'm kind of wanting to like get it in shape on Windows first, because when you do cross-platform, you have to make some kind of tough decisions about, what am I maybe giving up by abstracting it, and like, am I giving up performance? Am I giving up some kind of expressivity? And by doing the Windows native one first, then you can actually have that as a basis of comparison and say, okay, here's the cross-platform version. Does it perform the same? You can do benchmarks, etc.
Sorry, one other question. So you mentioned that one of the impetus for this was being high performance, right? You want a high performance GUI toolkit. So I'm curious what the current performance bottleneck is in running the entire layout and painting engine, as well as generally what the experience of performance debugging is, figuring out what these bottlenecks are, and if you have any experience in other GUI toolkits, how that contrasts.
So performance in GUI toolkits is a really difficult, deep question, and especially on a lot of different axes. And a lot of times people will focus on just one, like the ability to do smooth 60 frames a second updating. And like that's probably not where most of the pain is. Probably most of the pain is in things like startup, time and like transition from one activity to another kind of thing. And in those things, you get all of the cost in things like inflation of your widget tree, and so on and so forth. But it's also true that just scrolling is performance intensive, and then you get into so there's scrolling, which just requires traversing getting your painting done really fast. Which, like, I could talk all night about this. I'm trying to think how do I distill this into a way that's useful. Then there's this business which is on the screen now, which is minimal invalidation. And minimal invalidation means that if you press a key and the key inserts a character, that you do not repaint the entire screen from top to bottom, that you only address the specific area that got updated. Or in my case, I'm doing line granularity because trying to do it finer than that just isn't worth it. So there's this principle of, like one of the principles of UI performance is do as little work as possible. So you can really look at the system from the outside as saying there's some input and there's some output, which is like drawing calls, and then there's all this stuff in the middle. And if there's a huge amount of stuff going on in the middle, or if there is a lot more drawing calls than you actually needed to update the state to its new appearance, then that is performance, potential to improve the performance. So this is definitely, and minimal invalidation, this is something that GUI toolkits used to do, because if you were repainting the screen, it would visibly take longer than one VSync. So it's kind of fallen out of favor a little bit, but I think it's still really interesting and important to do, if for no other reason than to reduce battery consumption, power consumption, because just doing this tiny amount of work is going to consume less GPU bandwidth and stuff like that. So that's a real goal, and that I've identified as a real problem. I mean, if you put one of these other editors, I won't name them, the ones that are implemented using web toolkits underneath, then you see this tremendous amount of work that's happening just in response to like pressing a key. So then, this goes, I'm not going to go into all the details, but I've thought through what do you need in this data-oriented world to do minimal invalidation? Like, how do you keep track of that state? How do you do all of these processes so that when you're done, you're only drawing, updating some small region? And I think that's definitely one of the opportunities that, especially if you look at kind of immediate mode and some of the other things that are maybe a little bit more like game engine UIs, that they tend not to give you that opportunity.
Would you be so kind as to go back to your cross-platform bonus slide?
Sure.
Based on my memory, an astute observer might comment that these two top-level bullet points are basically the beginning motivations in the Flutter rendering pipeline talk you linked to, if I remember correctly.
I'm not sure that's
fair. I may be thinking of a different one.
Yeah, that might be, because Flutter, Flutter, if you actually look at Flutter, Flutter is using Skia as the kind of provider of these abstracts. Actually, it's more complicated than that, because it's using Skia for the 2D abstraction, and then for text layout, there's a very interesting story here where that used to be an adapted version of Blink's text layout engine, which was very much web, based. And they finally, ripped that out and replaced it with something else called libtxt, which I think is very interesting because it really is a focused, how do you solve the modern text layout problem, which means text layout with emoji, and solve these problems like how do you enumerate the fonts on your system so that when you actually choose a font, it's making roughly the same choice that the system font rendering would have done. So yeah, that's the layer. That's definitely layers below what you're going to see in the Flutter talk.
Right. So I must be remembering a different talk, but the Skia and libtext thing is what I'm thinking of.
Yeah.
So is your opinion that that's the main body of work? Because it seems like that's, aside from the bits in Dart, that seems like the largest chunk of Flutter, right? Is just getting boxes onto the screen. So is that actually could you run your Xywin GUI on top of those abstractions conceivably? And have you looked at it yet?
Conceivably, absolutely. I have looked at it. And so the thing, kind of one of the observations is, so Skia is a very large, heavyweight dependency in a lot of different ways. So for example, if you git clone Skia and its dependencies, I forget exactly, it's some hundreds of megabytes. And it will take a long time to compile. And so I feel when I say cargo run, and that happens in some reasonable amount of time, I feel like taking on a dependency to Skia kind of degrades that dimension. So if you are on Windows, then I think you really want to be using the Windows native drawing APIs, because those are good. On a different platform, Skia might be a really good choice. And so that's really why I'm specifically saying I want this to be an abstraction that gives you those choices. And then, I think Skia obviously works on pretty much every modern mobile and desktop platform that you might care about. So that would be a good thing to do. If you had that, then it would kind of fill the matrix where at least you had a workable solution, even if it wasn't ideal in all respects, of which, kind of compile time size of dependency is one that it's kind of not good.
So is what you're saying then that you think choosing to abstract across the platforms at that layer in the stack is not appropriate for a text editor? Or, I'm trying to parse that last. It would do a very good job of filling the matrix, but on Windows you want to be doing this.
Yeah, I'm not sure what you're asking.
Why didn't you use Skia, I guess?
Why didn't I use Skia?
Yeah, aside from the cargo run thing. Is that the only reason?
I mean, I think it's a pretty compelling reason.
Yeah.
And the other reason not to use Skia is that Skia's API is C++. Right. And there is extra work. It's not impossible, but there is extra work that needs to be done to make that kind of smoothly interoperate with Rust. And that work is not in really good shape. Like there's Servo used to use Skia. Servo used to have a Skia binding, and then that's being replaced by WebRender. And honestly, like I need to be a little bit careful because so many of these people are my colleagues and stuff like that. But let me just phrase it this way, that I actually find WebRender dependency to be kind of a really interesting direction to go with this abstraction as well.
Right. Thank you. So, sorry for the confusion question.
Oh, no.
Yeah.
Maybe one or two questions?
No, you've got to have more.
No, everyone already asked my
Oh,
question.
okay.
All right. Well, thanks everybody for coming.
Thanks all for coming. As always, we've still got quite a bit of time, so feel free to hang around. If you're interested in speaking at one of the future meetups, let me know. And like I said, the next meetup will probably be in Stanford. There will be updates on the meetup page, probably in the middle of July. All right, thank you.